Hello and welcome. In this video, we will explore the properties of curves using calculus. This topic is a core component of the IB Mathematics Analysis and Approaches higher-level curriculum. By the end of this session, you will be able to use the second derivative to determine the concavity of a function, identify and classify points of inflection, and apply these concepts to sketch complex functions. We've previously seen that the first derivative, f prime of x, gives us the gradient of the curve. Today, we'll focus on the second derivative, f double prime of x, which tells us about the rate of change of the gradient. This information is crucial for understanding the shape or curvature of a function. Let's begin with the concept of concavity. A curve can be concave up or concave down. A curve is concave down on an interval if its shape resembles an inverted U. This means that as you move along the curve from left to right, the gradient of the tangent line is continuously decreasing. For example, consider the function f of x equals negative x squared. The gradient of the tangent starts positive, becomes 0 at the peak, and then becomes negative. The gradient is always decreasing. Mathematically, a decreasing gradient means that the first derivative, f prime of x, is decreasing. And a decreasing first derivative means that its own derivative, the second derivative, f double prime of x, must be negative. So, a curve is concave down when its second derivative is less than or equal to 0. Conversely, a curve is concave up on an interval if its shape resembles a U. Here, as you move from left to right, the gradient of the tangent line is continuously increasing. For the function f of x equals x squared, the gradient starts negative, becomes 0, and then becomes positive. The gradient is always increasing. An increasing gradient means f prime of x is increasing, which in turn means its derivative, f double prime of x, must be positive. Therefore, a curve is concave up when its second derivative is greater than or equal to 0. To summarize, the sign of the second derivative tells us the concavity of a function. A negative second derivative means concave down, and a positive second derivative means concave up. Let's work through an example to see how this is applied. We will find the intervals where the curve y equals 2x cubed minus 3x squared plus 4x minus 6 is concave up or concave down. Our objective is to determine the concavity of this cubic function. The first step is to find the second derivative. We start by differentiating once to find the first derivative. The first derivative, di by dx, is 6 squared minus 6 plus 4. Now we differentiate again to find the second derivative. The second derivative, d squared y by dx squared, is 12x minus 6. We can factor this to 6 times the quantity 2x minus 1. To find where the concavity changes, we need to find the values of x for which the second derivative is 0. Setting the second derivative to 0 gives us 12x minus 6 equals 0, which solves to x equals 1/2. This value, x equals 1/2, is a potential point of inflection, which we will discuss in more detail later. For now, it divides the number line into two intervals. We can use a sign diagram for the second derivative. We test a value in each interval. For x less than 1/2, say x equals 0, the second derivative is negative. For x greater than 1/2, say x equals 1, the second derivative is positive. Based on our rules for concavity, we can now state our conclusion. Since the second derivative is negative for x less than 1/2, the curve is concave down on that interval. Since the second derivative is positive for x greater than 1/2, the curve is concave up on that interval. So we have successfully used the second derivative to determine the concavity of the function. Now let's introduce the concept of a point of inflection. A point of inflection is a point on a curve where the concavity changes. This means the curve changes from being concave up to concave down, or vice versa. A key property of a point of inflection is that the tangent line at that point crosses the curve. Visually, you can see the curve changing shape. The tangent line, called the inflecting tangent, passes through the curve at this point. Mathematically, a point of inflection occurs at x equals a if two conditions are met. First, the second derivative at that point must be 0. Second, the sign of the second derivative must change as we pass through x equals a. This change in sign is what indicates the change in concavity. It's important to note that f double prime of a equals 0 is a necessary condition, but not sufficient. The sign must change. For example, For the function f of x equals x to the power of 4, the second derivative is 12x squared. At x equals 0, the second derivative is 0. However, for x less than 0, it's positive, and for x greater than 0, it's also positive. The sign does not change, so x equals 0 is not a point of inflection, but a local minimum. Points of inflection can be further classified based on the gradient of the tangent at that point. If the tangent at the point of inflection is horizontal, meaning the first derivative f prime of a is also 0, we call it a stationary inflection point. At a stationary inflection point, the gradient is 0, but the curve continues in the same direction. For example, it might increase, flatten out, and then continue to increase. The sign diagram for the first derivative would show no change in sign, while the sign diagram for the second derivative would show a change in sign. If the tangent at the point of inflection is not horizontal, meaning the first derivative f prime of a is not 0, we call it a non-stationary inflection point. Here, the curve changes concavity, but the gradient is not 0. The tangent line is sloped. The sign diagram for the first derivative would show a change in sign, indicating a local maximum or minimum, while the sign diagram for the second derivative would show a change in sign. So, to classify an inflection point, we first confirm it's an inflection point by checking the second derivative, and then we check the first derivative to see if it's stationary or non-stationary. Let's apply these ideas to a more complex function. We will analyze the function f of x equals 3x to the power of 4 minus 16x cubed plus 24x squared minus 9. Our goal is to find and classify all stationary points and points of inflection, and then use this information to sketch the graph. First, let's find the stationary points by setting the first derivative to 0. The first derivative is 12x cubed minus 48x squared plus 48x. Factoring out 12x gives us 12x times x squared minus 4x plus 4, which simplifies to 12x times the quantity x minus 2 squared. Setting this to 0 gives us stationary points at x equals 0 and x equals 2. Now, let's classify these points using a sign diagram for the first derivative. For x less than 0, f prime of x is negative. For x between 0 and 2, f prime of x is positive. For x greater than 2, f prime of x is also positive. The sign changes from negative to positive at x equals 0, indicating a local minimum. At x equals 2, the sign does not change, which suggests a stationary inflection point. The coordinates are 0, 9 for the local minimum and 2, 7 for the stationary inflection point. Next, let's find and classify the points of inflection by analyzing the second derivative. The second derivative is 36x squared minus 96x plus 48. We can factor out 12 to get 12 times the quantity 3x squared minus 8x plus 4. Factoring the quadratic gives us 12 times x minus 2 times 3x minus 2. Setting the second derivative to 0 gives us potential inflection points at x equals 2 and x equals 2/3. Let's use a sign diagram for the second derivative to check for a change in sign. For x less than 2/3, f double prime of x is positive. Between 2/3 and 2, it's negative. And for x greater than 2, it's positive. The sign changes at both x equals 2/3 and x equals 2, confirming they are both points of inflection. We already classified x equals 2 as a stationary inflection point because f prime of 2 was 0. Now let's classify x equals 2/3. We need to find the first derivative at x equals 2/3. Substituting into our factored form, we get 12 times 2/3 times negative 4/3 squared, which is 128 over 27. Since this is not 0, the point at x equals 2/3 is a non-stationary inflection point. The coordinates of this non-stationary inflection point are approximately 2/3 negative 2.48. Now we have all the information needed to sketch the graph of f of x equals 3x to the power of 4, minus 16x cubed plus 24x squared minus 9. Let's summarize our key features. A local minimum at 0, 9, a non-stationary inflection point at approximately 0.67, 2.48, and a stationary inflection point at 2, 7. We can also use our sign diagrams to determine the intervals of increasing, decreasing, and concavity. The function is decreasing for x less than 0 and increasing for x greater than 0. It is concave up for x less than 2/3 and for x greater than 2. It is concave down between 2/3 and 2. Let's put this all together on a graph. We start by plotting our 3 key points. The curve decreases to the local minimum at 0 and 9. From there, it increases, but its concavity changes from up to down at the non-stationary inflection point. It continues to increase, but now concave down, until it reaches the stationary inflection point at 2, 7. At this point, the gradient is 0, and the concavity changes back to up. The curve then continues to increase, concave up, for all x greater than 2. This detailed analysis allows us to create an accurate sketch of the function, showing all its important features. Let's look at another example, this time involving an exponential function. Consider the function y equals 2 minus e to the power of negative x. We will find its intercepts, concavity, asymptotes, and then sketch the graph. First, the intercepts. For the y-intercept, we set x equals 0. I equals 2 minus e to the power of 0, which is 2 minus 1, or 1. The y-intercept is at 0, 1. For the x-intercept, we set y equals 0. 0 equals 2 minus e to the power of negative x. This means e to the power of negative x equals 2. Taking the natural logarithm of both sides, negative x equals ln 2, so x equals negative ln 2. The x-intercept is at ln 2, 0. Next, let's find the concavity using the second derivative. The first derivative is e to the power of negative x. The second derivative is negative e to the power of negative x. Since e to the power of negative x is always positive, the second derivative is always negative. This means the function is concave down for all real values of x. Finally, let's consider the horizontal asymptote. We examine the limit as x approaches infinity. As x approaches infinity, negative x approaches negative infinity. E to the power of negative infinity approaches 0. So y approaches 2 minus 0, which is 2. The horizontal asymptote is y equals 2. Now we can sketch the graph. We draw the horizontal asymptote at y equals 2. We plot the intercepts. The function is always concave down and approaches the asymptote from below as x increases. This gives us the complete sketch. Let's conclude with a summary of the key concepts we've covered. We've seen that the first derivative, f prime of x, tells us about the gradient and whether the function is increasing or decreasing. The second derivative, f double prime of x, tells us about the rate of change of the gradient, which determines the concavity of the curve. A positive second derivative means the curve is concave up, while a negative second derivative means it's concave down. A point of inflection is where the concavity changes. This occurs when the second derivative is 0 and changes sign. If the first derivative is also 0 at this point, it's a stationary inflection. Otherwise, it's a non-stationary inflection. By combining the information from the first and second derivatives, we can perform a comprehensive analysis of a function's behavior and create an accurate sketch of its graph. This is a powerful tool in calculus for understanding the properties of curves. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video and try to solve them on your own before looking at the solutions. Question 1. Find the intervals where the function f of x equals x cubed minus 6x squared plus 9x plus 1 is concave up or concave down. Question 2. Find and classify all points of inflection for the function y equals x to the power of 4 minus 6x squared plus 10. Question 3. Consider the function f of x equals ln of 3x squared. Find the domain. Draw the sign diagrams for f prime of x and f double prime of x and sketch the graph. Question 4. The surge function is given by f of t equals ate to the power of negative bt, where a and b are positive constants. Prove that the function has a local maximum at t equals 1 over b and a point of inflection at t equals 2 over b. Question 5. Consider the logistic function f of t equals c over 1 plus ae to the power of negative bt, where a, b, and c are positive constants. Prove that if a is greater than 1, there is a point of inflection with a y-coordinate of c over 2. Let's go through the solutions. Here's the solution for question 1. We start with the function f of x equals x cubed minus 6x squared plus 9x plus 1. The first derivative is 3x squared minus 12x plus 9. The second derivative is 6x minus 12. We set the second derivative to 0 to find the potential inflection point. 6 minus 12 equals 0, which gives x equals 2. The sign diagram for f double prime of x shows a change from negative to positive at x equals 2. Therefore, the function is concave down for x less than 2 and concave up for x greater than 2. Here is the solution for question 2. We are given the function y equals x to the power of 4 minus 6 squared plus 10. The first derivative is 4x cubed minus 12x. The second derivative is 12x squared minus 12. We set the second derivative to 0. 12x squared minus 12 equals 0, which gives x squared equals 1, so x equals plus or minus 1. The sign diagram for the second derivative shows a change in sign at both x equals 1 and x equals 1, confirming they are both points of inflection. Now we classify them. We need to check the first derivative at these points. At x equals 1, the first derivative is 8, which is not 0. So 1, 5 is a non-stationary inflection point. At x equals 1, the first derivative is 8, which is also not 0. So 1, 5 is also a non-stationary inflection point. Here is the solution for question 3. We are given the function f of x equals ln of 3x squared. First, the domain. The argument of a logarithm must be positive. Since 3x squared is always positive for any non-zero x, the domain is all real numbers except x equals 0. Using the chain rule, the first derivative is 2 over x. The second derivative is negative 2 over x squared. The sign diagram for f prime of x shows it's negative for x less than 0 and positive for x greater than 0. The sign diagram for f double prime of x shows it's always negative for x not equal to 0. This means the function is decreasing for x less than 0 and increasing for x greater than 0. It is concave down for all x in its domain. The graph has a vertical asymptote at x equals 0. The sketch shows a curve that is symmetric about the y-axis, concave down everywhere, with a vertical asymptote at x equals 0. Here's the solution for question 4. We need to prove the properties of the surge function f of t equals a te to the power of negative bt. First, let's find the local maximum. We need the first derivative. Using the product rule, the first derivative is ae to the power of negative bt minus abt te to the power of negative bt. Factoring gives ae to the power of negative bt times the quantity 1 minus bt. Setting the first derivative to 0, we find that t equals 1 over b. Since a and b are positive, the sign of f prime of t changes from positive to negative at this point, confirming it's a local maximum. Next, let's find the point of inflection. We need the second derivative, differentiating of prime of t. Using the product rule again, we get f double prime of t equals abe to the power of negative bt times the quantity bt minus 2. Setting the second derivative to 0, we find that t equals 2 over b. The sign of f double prime of t changes from negative to positive at this point, confirming it's a point of inflection. We have successfully proven both statements. Finally, here's the solution for question 5. We need to prove a property of the logistic function f of t equals c over 1 plus ae to the power of negative bt. We are looking for a point of inflection, so we need the second derivative. Let's rewrite the function as c times the quantity 1 plus ae to the power of negative bt, all to the power of negative 1. Using the chain rule, the first derivative is c abe to the power of negative bt divided by the square of 1 plus ae to the power of negative bt. Now for the second derivative, we use the quotient rule. After applying the quotient rule and simplifying, we find that the second derivative is 0 when the numerator is 0. This occurs when ae to the power of negative bt equals 1. Solving for t, we get tt equals 1 over b times ln of a. Since a is greater than 1, ln of a is positive, so t is positive. The sign of the second derivative changes at this point, confirming it's an inflection point. Finally, We find the y-coordinate of this inflection point by substituting back into the original function. The y-coordinate is c divided by 1 plus ae to the power of negative b times 1 over b ln of a. This simplifies to c divided by 1 plus a times 1 over a, which is c over 2. We have proven that the y-coordinate of the inflection point is c over 2. That concludes our exploration of concavity and points of inflection. We have seen how the second derivative is a powerful tool for analyzing the shape of a curve and identifying its key features. Mastering these concepts is essential for success in IB Mathematics AAHL. Keep practicing with a variety of functions to build your confidence and problem-solving skills. Thank you for watching.